section 8.1, vectors. So I came up with a way of going about this. I didn't like how I had done it before. So first, since I'm talking about vectors, I'm going to bring up a term called the scalar. What's a scalar? It's just a number. It's just a number. So why do we even have this term? I think the reason is because when you start talking to scientists and they start talking about quantities that are vectors, sometimes you have a quantity that is not a vector, it's just a number, and instead of just calling it just a number, they gave it this name, scalar. I guess it's not just a number, it's a number measuring something. I mean, we can measure things with numbers, but... So, examples of scalars are like temperature. Or weight. Or for those of you who are already taking physics, mass, which is different. Height of something. You can kind of think of your favorite measurement, the scalar. All right. Let's think about something which might not be just a scalar. Position. Now, we're on a real number line. It's a scalar. But we might be on a x, y axis, or three dimensions. We have 3 coordinates. So, it's not just one number. Talk about velocity. What's velocity? If something's moving, it's I'm going to call this x. Velocity is x per time. How far is it moving per unit time? And again, you've taken a physics class, this is old hat. Acceleration. That tells you how your velocity is changing with time. So with these 3 things in mind, I'm going to throw an imaginary ball. This is, I guess it could be a missile or a spacecraft. This is its trajectory. This is time. So over time, it goes from one place to another. And you might be here at, we'll call it the origin, watching this happen. So you might recognize that there's some distance from you. And this is position. There's also an angle here. And as this object we're throwing moves, its position changes. And then we get another angle here, and so forth, all the way around. Now, if we take a look at this object, we look at where is it going at a particular moment, right? So, we're going to use an arrow here, and assuming this is also, we're throwing this, in a parabolic shape. This also has some angle associated with it. As it moves, this velocity is going to get smaller and smaller until we hit the top, and then it's going to start getting larger and larger as it moves down. And finally, if you think about this velocity, how the velocity is changing, well, if you think about why it's changing, it's because something's pulling it down. We call that force of gravity. And that has a direction too. That's pulling it down towards the center of the Earth. This is the acceleration. As it turns out, until you get pretty far away from the Earth, the acceleration is pretty much the same. It's, again, it's about 10 meters per second squared. So, you know, we have these different quantities here that they have a direction and a magnitude. And that's the idea behind a vector. It's not a scalar, it just has a number. A vector has a direction or angle, and it has what we call a magnitude. Magnitude itself is a scalar, just a number. And we represent it as we draw a straight arrow. We put a little arrowhead on it so you know the direction. I mean, if I just drew a line segment, well, maybe it's down in that direction, up in that direction. But we draw a head on this arrow so you know which direction it's going. And I want to emphasize this is a mathematical object to model something or represent something. You know, if I throw the chalk, you don't see little arrows. You just have to kind of see them in your head. That's what's happening. Since I have this nice little diagram here, I'd like to just point out a curious, it's kind of a curious physics thing. Let's say this is the Earth. And we, you know, we're over here in Cape Canaveral, and we fire off a rocket, and it goes into orbit. So just as in this diagram, I mean, there's a position. You take the origin, the center of the Earth. Position is just kind of moving around like this. The velocity turns out to be perpendicular to the position vector. And the acceleration, which is always towards the center of the Earth, is just in the opposite of the position. So you have something rotating around, you're like holding it with a string. Constantly, the change in your velocities towards, you know, that center that you're pulling from. I guess that's a little ahead of things. All right. What? I just want to throw out a piece of vocabulary in case it comes up in any of the problems. This is from physics. What we call velocity is a vector. But we often talk about something which is the speed of something. And the speed is just the magnitude of the velocity. It's kind of a velocity vector without the vector. That's just a terminology. Typically, we only refer to velocity, the magnitude of velocity as a positive value. Since something can be moving in either direction, the two vectors would differ by their direction, whereas you could have a negative speed. You know, you could talk about the speed of a car, and if it goes in reverse, it has a negative speed.
Wait, so just to clarify, direction is like the attribute that makes something a vector?
I think you're on the right track, but I wouldn't use that term. What I would say is a vector is a magnitude and a direction. So if you want to say I had a magnitude and I added a direction, it became a vector, yeah, that's okay. All right, so, okay, the clear things. Clear my head. Okay, so we have this thing, we call it a vector, and we represent it by a line. Again, we put a little arrowhead on the top, call that the head. And the origin, where it comes from, we call the tail. And so we can represent this vector by a set of points. All right, we could call this, I don't know, let's call this 4, 3. And so another way to represent this algebraically would be to just write the points and put a little arrow between them. Here we run into a feature of vectors. Vectors don't have a location. Like this is, I'm writing this vector at a particular location. But a vector, again, is just the magnitude and the direction. So I can move this around, like draw nicely, and it's still the same vector. So one way to translate this is just simply to adjust x. No, we won't use x, we'll use d. Some distance. I'm going to use E here, because this could be a different, we can move it sideways or up and down. But a nice way to represent this is by moving the tail to the origin. And in this example, that's pretty easy. I just 1 minus 1, 1 minus 1 goes to 4 minus 1, 3 minus 1. So now we have a vector 0, 0 to 3, 2. And we have a simplified way of writing this. We can use our greater than or less than brackets and write it this way. So this is just a vector with a head at 3, 0 and a tail at 0, 0. All right, so now, let's say I have some position vector. I start at some point, and I guess we'll just do this in one dimension. It's got a magnitude of 4. And then, just the position. It's like where I am. And I move it direction 3. Obviously, my new vector is just a vector now with 4 plus 3 or 7. So if two vectors are going in the same direction, you can add them by just adding their magnitudes. On the other hand, if I had a vector where I'm going in some direction, 2 dimensions, and then I go in a different direction, well, where I end up in a new location, and so let's call this U and V. So I end up at U plus V. I also just want to remark on how you're going to see vectors referred to in print. You're either going to show it by putting a little arrow on top, like this, or they might use boldface. I don't know how to do that on Blackboard. And sometimes they'll just put a line over it. And again, that's to make it look different than just a variable where you put a number. All right, so the point here is you can add vectors graphically by simply putting the tail of one at the head of the other and getting the new vector as going from the original tail to the new head. Now, this is sometimes known as the parallelogram law. You can think about it this way. You could draw a parallelogram here, and either way you add it, it's the same. Is to say that U plus V is the same as V plus U, which is to say vector addition is commutative, just like for numbers.
What would that look like if you had numbers, like you had coordinates there?
Well, that was the next thing I was going to do. But I think we're going to take a break for a few minutes, and then you can remind me if I haven't started doing that. That's what we're doing next. All right? Okay. Yes? Excellent question. That I want. So let's bring it up then. Also, these aren't going in the same direction.
They aren't.
They aren't.
Oh.
This one's going here, this one's going there. But I know what you're thinking. This is going to go there.
Yeah.
It's coming.
Okay.
You're ahead. I feel like somebody came in after class started.
He's good.
I don't see them. that were things that were coming. Let's see, I think the first one was, well, how can I do that? I mean, I have two vectors, we'll call them, I don't know, 2, 2, and 3, 3. We want to add them, so let's see. So, 2, 2, that's one of my vectors. And, no, I don't want 3, 3, that would be too easy. 3, 5. 1, 2, 3, 1, 2, 3, 4, 5. So this is 3, 5, 2, 2. Okay. So what I want to do is it'll look better. So what I want to do is move this vector here, or move this vector here. So 4, 2 is what? It's 0, 0. To 4, 2. So I want to move this vector, I want to move its tail, 0, 0, to this head. So I'm going to add 3 and 5. So 0 plus 3, 0 plus 5. And I have to do the same here. 4 plus 3, 2 plus 5. That's 3, 5, 2, 7, 7. Okay, so I'm moving this here. So it's going to start at 3, 5 and go to 1, 2, 3, 4, 5, 6, 7. And then 1, 2, 3, 4, 5, 6, 7. Or I can take this vector, move it the same way, and I end up in the same place. That is to say, if I put my vectors in this form, which we call a position, I guess I should give it a name, these are position vectors. That is, their tail is at the origin. All I need to do is add their coordinates. So there's kind of a standard exercise that you get in this class, this kind of class, where you get graph paper and you add vectors by doing this kind of trick using this parallelogram law. But in fact, you only do that when you're first learning it. It's so obviously easy to add vectors just by adding the head coordinates. Does that answer your question? Okay. All right. The second question, an excellent question, came up. Well, what if I have like 4 and then 3 in this direction? Well, I could do the same thing. I mean, I could say this is 0, 0 to 0, 4. This goes from 4, 4 to 0, 4 to where? 0, 1. So when I add these together, I just get 0, 0, 2, 0, 1. Now, that's kind of graphically. It's a better way to think of this. We're going to get a better way to think about adding vectors that are going in the opposite direction in a minute. So okay, so we saw that you can add vectors quite easily. You just, put them in, write them as position vectors and add their coordinates. There's another operation you can do with a vector. If I have a vector, say, 0, 0 to 3, 5, which I'll write as 3, 5. Okay. So, 3, 5. You can multiply vectors by a constant. So, I call this V, say like 2V. Well, what would that be? That would be like adding this vector to itself. And how would I do that? Well, 2V is just going to be 2 times 3, 2 times 5, 4, 6, 10. So now we have two operations on vectors. We can add them, and we can multiply them by a constant. Now, this of course brings up the question, what would -1 times v be? Well, that would just be taking v and reversing its direction. So this would be like -v. So if you want to take two vectors and subtract them, just like with numbers, you can think of that as adding the reversal of the second of the vector you're subtracting. Now that has an interesting graphical representation, which I want to point out. Just going to do this without without axes. So if I have a vector v, and I add it to a vector w, again, I get this kind of parallelogram kind of thing. And v plus w is the diagonal here. All right. What if I want to add v plus, I want to subtract v w from v? Again, that's adding negative w. Well, it's negative w. It's a vector. It's just v in the opposite direction. So if I add v to negative w, I'm I'm going to get a vector here. With a little imagination, you can see that's just the other diagonal of the parallelogram. So now we have three operations on vectors. We can add them, we can subtract them, we can multiply them by a constant. This brings up just one important point. What happens if I add v to negative v, or subtract v from itself? So I kind of have a vector here, it goes back here, and I'm kind of stuck. My head and my tail are in the same place. So this is a very important vector. This is called the zero vector. You can add the zero vector to any other vector and get the vector back again. Does anyone call it? We call that when we're dealing with numbers. You have a name, special name for the number that you add to other numbers and get your number back, aside from zero. It's the identity. This is an identity element for vector addition. And it has one really peculiar property. It doesn't have a direction, or if you like, it has any direction. Okay, so let's see. Where am I? Okay. It might be useful just to give this some reality here. Let's just look at, what a typical application would be. Let's say you're flying from San Francisco, and let's just make believe LA is due south. So you would point your plane this way. But as it turns out, there's a crosswind, which we can express as a vector. So, you're going 100 miles per hour. The wind's going, we'll say 10 miles per hour. And instead of ending up in LA, you end up over here in the middle of the ocean somewhere. So, how are you going to correct that? Well, you need something to counteract the direction of the wind. So you need, have a vector 10 miles per hour in the other direction, and you have to point your plane in that direction. So you head, toward, I guess Vegas is out here. And you fly towards Vegas, and you end up in LA because the wind blows you over. So here we are adding two velocity vectors. Okay. All right. If we have a vector and we describe it by these coordinates, how can we find the magnitude just from this representation? Well, we're going to use the Pythagorean theorem here. And we're going to see that the magnitude of the vector, which we're going to write this way, is just the square root of here, a squared plus b squared. Pretty straightforward. This use of vertical bars is very similar to absolute value. There's situations where you can kind of forget whether you're dealing with a vector or a number. But if you know it's a vector and it has more than one coordinate, you're going to need to use the Pythagorean theorem. I don't know if we'll get into three-dimensional vectors. That would be x, y, and z. Then the magnitude formula would just extend. It's kind of the extended Pythagorean identity theorem. Okay, we talked about multiplying the vector. Distributing the scalar or multiplying it by over the coordinates. We mentioned you add a vector to the zero vector to get the vector back. Talked about subtracting vectors. Okay, so at this point, we're going to look at this from a kind of a pure math point of view. We're just going to say, okay, we have this thing called a vector, and we can do things with it. It seems to have some properties. So we're going to write them down just to kind of see how they compare with regular numbers. So, first property is that if we have two vectors, we can get a vector. That's kind of what I'm trying to indicate here. This is the property we call closure. Think of numbers. You can take any two numbers, you can add them, you get a number. V plus u is equal to u plus v. So we have the unity property. Now, if you think about how we add vectors, which is by adding their coordinates, I don't have that up here, but it's pretty easy to see that this is going to be associative exactly because numbers are associative. And we saw that there's an identity property. And going a step further here, I think we saw that if you add v and negative v, you get the identity. Well, this is exactly the property we call the inverse property. So, just like numbers, with respect to addition, we have all the same properties. That might want to think about this. Gee, can we divide vectors? Can we multiply vectors? Okay. We'll talk about that on Thursday a little. But we do have some other properties here that are not something you have with regular numbers because vectors are different. We saw that you can multiply a vector by a scalar. I guess we're going to use k for a scalar or a number. But with a little work, we can show that we have a distributive property. We can distribute this multiplication over this sum. So this is a distributive property. Similarly, use K and L. If we're distributing the sum of some numbers, if we have the sum of two numbers that we're multiplying by a vector, that can distribute also. These are both distributive properties, but they're very different. Here I have two vectors. Here I just have two numbers. When multiplying by scalars, there's an identity. Again, this is an identity property. We have an identity for multiplying by scalars. There's the zero property, which this is, I guess that we have something like this for numbers, but it's just multiplying two numbers. This is not multiplying a number, 0 times a vector, and we get the zero vector. But likewise, if we multiply some scalar, some number, by the zero vector, unsurprisingly we get the zero vector. So these are somewhat different properties that we get with vectors. And finally, the last property in this list has to do with the magnitude of a vector. We're giving this yet another name. We could call it the magnitude, or sometimes we use the word norm of a vector. And the property is that the norm of some scalar times a vector, here's where these vertical brackets can get a little confusing. That's equal to the absolute value of the scalar times the norm of the vector. Okay. The confusing part here is the vertical bars here, they intuitively mean the same thing, but they're actually different. This is just taking some number, like -1 is 1, or 3 is 3. But here we have a vector, and we're talking about the magnitude of the vector. Okay, just have a little more today. There's a lot of terminology today that goes along with vectors. Keep my vector, AE vector. So I can multiply this by a constant or divide by a reciprocal. If I take V and I divide it by the norm of V. Okay, so what am I doing here? I have a vector that has some length, some magnitude. I take that magnitude and multiply by 1 over that magnitude. Its new magnitude is going to be 1. So this new vector I created, I guess I'll write it this way, 1 over. I call this a unit vector. Pretty obvious. It has magnitude 1, size 1, or norm 1, a unit. Now, in particular, there are two very important unit vectors when we're dealing with x and y coordinates. We have a unit vector along the x-axis. That's 1, 0. I guess we're just going to call this x vector for a second. Y vector, that would be we give these special names. It's a little confusing. We don't call them x and y. We call them I and j. And likewise, if there was a z coordinate, we would call it k. Now, there's something annoying about this, which is we also use I to mean something completely different in mathematics. When we're dealing with complex numbers, we use it to mean the square root of -1. And this is very, very intentionally different. But there's something really useful about having these unit vectors. Which is, if I have some vector here, I can break it down in terms of these vectors. If I have some vector a comma b, I can break that down as a times 1, 0 vector plus b times 0, 1 vector. And I might write that a I plus b j. And now I have this b vector broken up into its components, the x component and the y component and the x component. This also has a name. This is called a linear combination. It's a linear combination of I and j, but it would still be a linear combination if there were other vectors. Some scalar times a vector plus some scalar times a vector. And I think we're going to talk about linear combinations on Thursday a little more. Okay, one last quick, well, hopefully not too quick. If you think about a vector from the point of view of trigonometry, so this is A, this is B. This here is going to be the norm of my vector, the magnitude of it. We can have formulas to go back and forth between this form and magnitude, and I guess I'll just put theta here. So they're the same formulas we've been looking at when we were looking at polar coordinates and when we were looking at complex numbers. The angle is the arctan or inverse tangent of y over x, or in this case d over a. And I think we already saw that the norm is square root of a squared plus b squared. If we want to go in the other direction, we want to start with theta and the norm. Let's call this m for magnitude. Then we would have a equals m cosine theta and b equals m sine theta. That's our main connection with trigonometry here. Again, call this m, and you can see that a times the cosine of theta is m, and m times the cosine of theta is a, and m times the sine of theta is e. That's our introduction to vectors. We're going to do a little more. There's one more piece to this puzzle that makes it a lot more interesting. And we'll cover that on Thursday. Thank you.